Another example, this is typically the one I briefly talked about before in terms of how to create the free body diagram correctly. Okay, let's look at this one. Again, a house frame support part of the roof. This is a part of the roof of a small building, because the whole building is not only this part, there's some other part, but we just consider a simplified version. The cable force is 150 kilonewton. The tension in the cable is 150 kilonewton. In other words, this is the cable. This, in fact, is a pulley, so that this and this are having the same magnitude, but different directions. Okay? And we know the tension or the magnitude of the cable is 150 kilonewton. Our job is to calculate the reaction at the fixed end E, point E. This is the fixed end. How are we going to calculate the reactions at point E? So again, for any of this kind of problem, number one, we need to plot, or we need to create the free body diagram. So in terms of creating the free body diagram, we need to go back to look at what we had. So either you can choose, this is wrong, point B, or you can choose point C. But obviously point B is the best one. Point C, you can do the same thing. Definitely correct, but you are just kind of duplicating these two forces, which are in the same direction, but in the opposite, in the same line, but in the opposite direction, always cancel out. So it really doesn't make any sense. Okay, so for this one, let's first plot the free body diagram. So this is the free body diagram. We have four forces, and you cut point E based on the fixed end. Correspondingly, you have a EX, EY, and the moment resistance. And this one, you have this cable. You really do not need to cut, because both point B and point D are within the rigid body. There's no need to cut. In between is no connection to outside. That's why you don't need to cut. However, this point D has another part of the cable connected to the ground. So you can cut at this point, or you can cut at this point. It doesn't really matter. For example, you cut very close to point F, you give a force, or you cut very close to point D, you give a force. That's the same thing. The reason this force acting on point F is equivalent to a same force acting on point D is because of what? This is called the principle of transmissibility in chapter 3. This one principle, they call the principle of transmissibility. You can move a force from one point to another one without doing anything else if you are moving along the force line. So that's why it's not a problem. You move to here, 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 it doesn't matter. So overall, this is what we call the free body diagram. So based on the free body diagram, we can always write down the three governing equations. And before we write down the three governing equations, what are those unknowns? We have EX, which is unknown, EY as another unknown, and the moment resistance we call ME is the third unknown. So again, in fact, we do not know whether this horizontal resistance is to the right or to the left. Doesn't matter. You assume to the right. Whether it's going up or going down, it doesn't matter. You assume going up. Even the moment resistance, you do not know is a clockwise or counterclockwise. You assume it's counterclockwise. And then we'll see what kind of result we're going to finally get. Okay? Based on this two-dimensional free body diagram, we can easily write down these three equations. Number one, all the x component forces equals 0. Number two, all the y component forces equals 0. And then number three, we're going to pick a point, and then we write down the moment at that point. So this and this and this are the three governing equations based on Newton's law. Then we just need to do step by step. Let's go back to look at the first one by collecting all the x component of forces and set equals 0. From this picture, what are those x components? These do not have any x component. Then forget about it. You have this one, EX. That's why you put the EX here. EX. And then this force, the cable force, has x component, because this one can be decomposed into x and y directions, right? So 150 times cosine of this alpha, or cosine of this angle. So let's say this angle is called alpha. Then cosine alpha multiplied by 150 should be the x component. Then what is a cosine alpha? This angle is the same thing with this one. Cosine alpha should be this. 4.5 divided by DE. But DE should be the square root of 6 squared plus 4.5 squared. So in other words, if you punch your calculator 6 squared plus 4.5 squared and square root, they should give you 7.5. So in other words, 4.5 divided by 7.5, that should be equal to cosine of this angle. Cosine of this angle multiplied by 150, that's the x component. So that's why cosine of this angle times 150, that is the x component of this cable force. And add them together, that's equal to 0. So that's the first equation. Second equation, by collecting all the y component and set it to 0. So go back to look at this free body diagram. Y component, you have 20, 20, 20, 20. All of them are going down. So that's why you get negative 20 plus negative 20 plus negative 20 plus negative 20, which is 4 times 20, but it's still negative. So this term represents these 4 small forces in vertical direction, all going down. So that's why I put a negative sign. You have EY, which is the y direction support. You put the EY here. So we collect this one, we collect this one, then we need to collect the y component of this cable. So y component of the cable, there's 150 times sine of this angle. Sine of this angle. Sine of this angle is supposed to be 6 divided by 7.5. So 6 divided by 7.5 times 150, that is a y component. But this y component is going down. If it's going down, you put a negative sign in the front. So now you add all of them together and set to 0. That's the second equation. Third equation, you need to collect the moment at a certain point. So which point you want to pick? Same thing. You want to find a point with more unknowns going through that point. Then obviously that's point E. If you're really picking point A, point B, there's really nothing wrong. But if you pick point E, that's much better. Yes?
For this problem, why isn't the weight accounted for?
The weight is not accounted, right?
The y.
Let me tell you, typically for slender members, we don't need to consider cell weight. However, if the problem does specify you need to consider cell weight, then you need to consider. For this problem statement, if you go back to look at this one, it doesn't say anything about the cell weight because this most likely is made of wood, the timber. So that's why the weight is very small. Then you don't have to. For any homework or some kind of assignment, if the statement said you need to consider self-weight, then you just need to consider. If the problem doesn't say anything about self-weight, you assume it's very small. Okay? And for any real structural engineering problems, any truss members, for any truss problem, we're going to talk about chapter 6, we never consider the self-weight because these are always built with the slender members. So it's relatively light. So that's why you don't need to consider self-weight. Any other questions? Okay, so move to here. We need to build the third equation, which is the moment equation at a certain point. So the reason we choose point E is simply because these two unknown forces are going through point E. So if you choose point E, then this EX or EY will not be involved in this equation. And that is something we want, right? We don't want to have too many unknowns involved in the equation. Okay, so now let's collect the moment of all forces at the point E, and that's equal to 0. First of all, what is the moment of this force at this point? F times D. F 20 times D. D is a shorter distance from this point to this force line. Then there's 1.8, 1.8, 1.8, 1.8 together. It's the 4 times 1.8, which is 4 times 1.8. Is that right? Where here? 4 times 7.2, right? So 7.2 is a shorter distance from here to this force line, and then don't forget to times the 20. So this is the magnitude of the moment of this force about this point. And then what is the direction? In other words, clockwise, counterclockwise. You hold this point, and then this force acting on here, it has a potential to rotate this rigid body counterclockwise. If you counterclockwise, you finally put the positive sign in front. Okay, so that's a contribution due to this force. How about the other one? You have another 20 acting on point B. What is the moment of this force at point E? So it's going to be 20 times the shorter distance D. That's from E to this force line. That's 3 times 1.8. 3 times 1.8 is 5.4. 20 times 5.4. This moment due to that force is also counterclockwise. So that's why I put the positive sign in front. How about this force? 20 times the shorter distance, 1.8, 1.8, that's 3.6. 20 times 3.6, that's a moment due to this force. It's also counterclockwise. That's why I put a positive sign. One more. You have a force acting on this point. What's the moment of this force at point E? So F times D. F is 20. D is a shorter distance. That's 1.8. So 20 times 1.8 is also counterclockwise. If counterclockwise, you put a positive sign. So these first four terms are the contributions of moment due to these four forces at this point. Okay? But we have other forces. What is the moment of this force, Ex, at this point? That's equal to 0, because passing through that point. The shorter distance equals 0. What is the moment due to this force at the point E? That's also 0, because this is passing through that one. The D, the shorter distance equals 0. Okay, so that's why you are not seeing Ey, Ex in this equation. We have the moment itself. So the moment itself, what is the moment due to this moment? Then of course you just add this moment. It's called moment E, which is unknown. But this moment is also counterclockwise. That's why you put a positive sign in front. Because counterclockwise typically is positive. Okay? So we have considered all the forces on this side, but don't forget, we have one more. What is the moment of this cable force? What is the moment of this cable force at this point? Okay? So the moment of this cable force at this point, again, is F times D. So what is F? F is 150, right? So what's the D? D is a shorter distance from this point E to the force line. So this is a force line. This is a shorter distance. Okay? And I'm going to show you later on using so this is a shorter distance, right? So what's the shorter distance of this one? It's going to be 4.5 times sine of this angle. 4.5 times sine of this angle. Sine of this angle equal to 6 over 7.5. So 4.5 times 6 divided by 7. Okay? 4.5, but they use a different way. I will explain to you this. But what I'm saying is if I can calculate the shorter distance, that's the same thing. So 4.5 times sine of this angle, 6 over 7.5 is sine times 4.5. That's a shorter distance. The shorter distance multiplied by 150, that's the moment. And this moment has a potential to rotate this rigid body at point E clockwise. That's what put the negative sign. If you cannot find the shorter distance, which is also fine, then you need to split this force into two components. This X component doesn't have a contribution because X component going through this point. Y component, what's the moment of Y component? Again, 4.5 times Y component. That's also this. Combining equation 1, equation 2, equation 3, you can solve for these unknowns. And then the problem gets solved.